Hi all. So this video is intended to produce the key for our at-home practice here. And so first thing you want to do is when you're trying to figure out if something is polar or nonpolar, go ahead and look at electronegativities and decide if something has polar bonds or nonpolar bonds. So let's go ahead and zoom in on our 4 compounds here. On the first one, fluorine is more electronegative than nitrogen. So there are going to be bond dipoles here, and they are going to be located or oriented in this direction. As you can see, that means that there's nothing in the opposite direction that's going to cancel out those bond dipole moments. So that means the nitrogen is going to end up a little bit positive. The fluorines are going to be a little bit negative. In the next structure, we know that nitrogen is more electronegative than hydrogen, so the bond dipole moments actually end up in the opposite direction. This means that the nitrogen is going to end up a little negative, and each of these hydrogens is going to have a slight positive charge. In formaldehyde here, oxygen is more electronegative than carbon. So you'll have a bond dipole moment in that direction. And so a partial charge of negative on oxygen and of positive on carbon. Now the carbon-hydrogen single bond is considered to be non-polar. And so we'll just make a little note of that. This is non-polar, so we can ignore it. It's not going to affect the overall bond dipole moment of the molecule. And then moving along to dimethyl ether here. Oxygen is more electronegative than carbon. And so we see that there's going to be a little bit of a positive charge on the carbons and a little negative charge on the oxygen. And so now we're going to go through each of these and see how they're going to interact with each other. And so we want to identify, is there going to be dipole-dipole, hydrogen bonding, ion dipole, or, well, I didn't write it on here, but London dispersion forces. And sometimes those are referred to as induced dipole types of attractions. And so, first off, London dispersion is going to be present in every single pairing that we have. As long as the species have electrons, it's going to have London dispersion forces. So it's not very informative to include those. As for ion dipole, none of these are ions, so none of them are going to have ion dipole. That intermolecular force is far more important once we get to Chem 116, and we're talking about things dissolving in water. So in the first case, we have nitrogen trifluoride interacting with itself. There are no hydrogens present, so hydrogen bonding is not present, but it's a polar molecule, so dipole-dipole will definitely be present. Moving on down, what we want to compare is the charges on the nitrogen fluoride or trifluoride versus the NH3, so the ammonia. And we could see that on the ammonia we have a polar molecule, just like the NH3, so dipole-dipole is definitely there. But also, more importantly, if we take a look at the ammonia, we can see that we have positively charged hydrogens. And when we have that, on one molecule, and a negatively charged fluorine on the next, we can actually have hydrogen bonding between them. Down here, for number 9, we could see that we have a negative on the oxygen, positive on the carbon, and so dipole-dipole is present, but no hydrogen bonding. Those hydrogens on formaldehyde don't have a charge. And then finally, number 13, that's going to be a dipole-dipole as well. So moving along, we're going to be taking a look at the hydrogens on ammonia compared to another ammonia molecule. Well, they're dipole-dipole, and because the hydrogens have a positive charge, that's hydrogen bonding as well. We don't need to do number 2 and number 3 because those are duplicates. Now let's compare for number 10. We have a negative charge on the oxygen of formaldehyde, and we have a positive charge on the hydrogens. So dipole-dipole for sure, and hydrogen bonding are going to be present. And now if we look at number 14, a similar story. The oxygen on the dimethyl ether could be attracted to the positively charged hydrogens in ammonia. So dipole-dipole and hydrogen bonding can be present. Now let's take a look at the formaldehyde with formaldehyde. Positively charged carbon, negatively charged oxygen. The hydrogens do not have any partial charge. They're nonpolar, so we can't have hydrogen bonding. Looking at number 15, similar story. We have positively charged carbons in both molecules, and then negatively charged oxygens in both molecules, so dipole-dipole is the only thing possible. And then finally, when we look at 2 ether molecules interacting, we have a negatively charged oxygen, a positively charged carbon, another positively charged carbon, and again, they're polar molecules, so dipole-dipole is present, but no hydrogen bonding.